Hello class, welcome to the final segment in lecture 26, and in this final segment we're going to talk about sort of a more specialized topic and sort of cover how our field of meteorology overlaps with the field of both structural engineering and urban development. And also our field also overlaps with aeronautical engineering as well, but we're not going to specifically cover that in this segment. We're going to actually talk more about more of an urban perspective on how meteorology overlaps with other disciplines. So with that, let's go ahead and dive right into it. So one thing that might be worth bringing up is one of the big time factors that urban planners have to account for when they're, say, zoning districts or deciding where a particular building should go. One of the big factors of that is the local wind patterns. And we'll see an illustration of this in not too long from now, but very shortly. That is to say, very shortly. But it's if you don't, you want to have a good idea of what the local wind patterns are in your specific area, because if you're, let's say you're trying to put it in some sort of industrial district where there might be a fair amount of air pollution being produced, you don't want the wind blowing all the pollution from that industrial district into a residential area, because one, the residents won't like that, and two, that can lead to adverse health effects if people are in their homes, which they are most of the time. They usually don't spend a lot of their time in other places. More of their time in other places. Majority of time is going to be at home. But at the same time, they're also going to be exposed to those pollutants a lot more if all these pollutants from, say, an industrial area or some sort of area with heavy pollution, some other activity that might be producing heavy pollution, you don't want all that nasty stuff winding up in a residential area where it is not going to be very welcome. So it's a good idea to know if you're going to be if you're planning a city or planning where to put industrial and residential districts, it's a good idea to take a good look at what your local wind patterns are going to be. You want to know what direction the wind comes from most often and what direction the wind comes from least often. And on the national scale, usually an easterly wind is least common. So if you take any point in the country, usually an east wind is going to be the least common wind direction when you take a look at the national average. However, that can vary very dramatically, because if you get down to near a coastal area where you might have to worry about sea breeze, that is wind coming in from the ocean, then suddenly an east wind might be relatively common compared to, say, somewhere in the plains where typically you've got two wind directions. South and north is usually not much in between. And if you live in the plains, you know exactly what I'm talking about. It's either a strong southerly wind or a strong northerly wind, occasionally a strong westerly wind, but usually the wind's either southerly or northerly, and that's pretty much it. There's not much variation in the wind direction there. But knowing something about what the patterns are in your specific geographic region, what the wind patterns are, can allow you to better plan your city so that you don't end up putting a lot of pollution in an area that a lot of people are living in. So that's just putting on the screen what exactly I just mentioned. But another thing another meteorological related topic that comes into more of a structural engineering and architecture perspective is how these wind patterns can influence the design and construction of not only just tall buildings, but also, say, suspension bridges. I know engineering students probably study this. This is probably one of the first things they're shown is the Tacoma Narrows Bridge up in Washington State, which it collapsed because it was subjected to a sustained strong wind, which caused the road deck to oscillate out of control, and eventually the structure could not take all the stress that was put on it, and then it just collapsed down into the river below. So it's knowing something about knowing what kind of winds that your structure is going to be subjected to can give you a good idea of what you should be planning for. And also in the realm of tall buildings, and by tall buildings I mean skyscrapers that are 30, 40, 50, 60, or many more stories tall. When you look at a skyscraper, it's got a massive surface area that if you subject a wind to that massive surface area, your building can take on a lot of force, and you got to make sure that the building's construction can tolerate all the force that's being subjected to it. And you can also find that it's not a linear relationship between the wind velocity and the force that's experienced. It's actually a quadratic relationship. So if you go from, say, 10 meters per second wind to a 20 meter per second wind, that doesn't double the force on the object in question, it quadruples it. So if you're going to be having those really strong winds, you want to make sure that, one, the structure is designed to tolerate the strong winds, but ideally you also want the structure to be facing in the direction of those winds, so that instead of, say, one anchor point bearing all the force, you've got two anchor points that are bearing all the force. And we'll see sort of an illustration of what exactly I mean by that. But also something that's related to urban development, and also to some extent to counterterrorism, is it's a good idea to know what the local wind patterns are in case there's some sort of industrial accident that releases some sort of toxic gas into the atmosphere, or maybe there's some sort of chemical spill, like an 18-wheeler or an oil tanker carrying some hazardous material gets into an accident and suddenly it's expelling all of its hazardous material into the air. You really need to know what the local wind patterns are, because if you're in a really dense urban area, say like a downtown district of a major city, you've got all these people that are in this downtown area, and if you want to keep them safe, you might have to order an evacuation. And if you've got tens of thousands or hundreds of thousands of people packed into this small area, you can't evacuate everybody. Try as you might, you're just going to end up with too much of a roadblock that no one's going to be able to get anywhere. No one's going to be able to get out of the way of the hazardous materials in time. But if you have a good idea of what the local wind patterns are, then you can know what areas are most likely to be affected by these potentially harmful chemicals, or if it's say like a bioterror attack, whatever the agent might be. It's a good idea. If you know what the local wind patterns are, then you can identify areas that are most likely to be affected and then evacuate those specific areas, and for the most part keep everyone safe in the process. If you evacuate a really small area, then you have a much better chance of getting everyone to safety than if you order an entire evacuation for the entire downtown area, which is just not going to work. There's just not enough capacity. The infrastructure just doesn't have the capacity to evacuate that many people in such a short amount of time. That's one of the reasons why. That's also one of the reasons why hurricane evacuations of dense urban areas are so tricky, because you have all these people that have to get from point A to point B in a relatively short amount of time. If you think normal rush hour traffic is bad, imagine getting every single citizen in your city from one place to another, as opposed to just the workforce. Imagine getting every single person from point A to point B. That can put an extremely high amount of strain on the traffic patterns. In fact, one of the more extreme examples of this occurring was the evacuation of Hurricane Rita, where some highways were literally parking lots for many hours because the traffic was just so incredibly dense. In fact, in that case, that was also occurring during a heat wave, and that was one case where the evacuation actually ended up killing more people than the hurricane, because people were stranded in the middle of nowhere. Their cars were out of gas, so their air conditioning wasn't worked, and they were just at the mercy of continuous strong heat. I believe the heat indices for that were like over 105 or 110. So it was kind of a disaster. So urban planning and meteorology are definitely overlapping, especially as population centers continue to increase. As urban areas become more populated, then this is going to become even more important to it's going to become even more important for meteorology to find its way into the role of urban planning. But now I want to go ahead and sort of illustrate some of the stuff that I've been talking about. So let's say that you've got some sort of configuration in your city that looks something like this. So let's say you've got a residential area and sort of near the center of the screen, and then out to the west you've got an industrial district. And let's say that in your specific region, on any given day, it is most likely that the wind is going to be coming from the west. Well, your citizens are not going to be very pleased, because this industry that might be producing a lot of pollution, all that pollution is going to be, on the vast majority of days, is going to be finding its way into the residential area, which is not going to be well received. And if you actually do plan that, then you might be voted out of office if you're the mayor of the city. But if you have this information at hand, then you can put the industrial district instead over here, so that the pollution is in fact, for the most part, being blown away from the residential area. And that way you can keep your citizens in your city much more happy, keep them much happier than if the pollutants on pretty much every day in the calendar year are making their way into their neighborhoods, which is not going to be well received. If you have a good idea of what sort of wind patterns are typical in your specific geographic region, then you can better accommodate for you can better accommodate for where you're going to put the industrial, the high polluting stuff. Usually that stuff just goes out in the middle of nowhere anyway, but you want to make sure that it is, on any given day, it is very unlikely that it will find its way into a residential area. And this also kind of goes back to what we were talking about when we were talking about pollution in the previous lecture. Ideally, you don't want dense urban areas to be resting in valleys because, as we've seen, valleys are great at creating stable air conditions, especially during the stable atmosphere, especially during the summer, because you get that layer of warm air that sits atop the valley, and that traps all the pollutants closer to the ground. So, ideally, if you can avoid that, that's also something that you want to account for. But this also, I also want to go ahead and illustrate what exactly I was referring to when I was talking about engineering, say, a large skyscraper. So there are several different terms for this, tailwind, headwind, and flank wind, but they're pretty much the same exact diagram, just drawn from a different perspective. And the key takeaway message that you want to see is if the black arrows are representing the wind that is being subjected to the building, then you can see how you're going to be pushing on just this face of the building, and the brunt of this wind is going to be endured by the two corners that are on the opposite end. And you can sort of look at this from different perspectives. So in this case, in this particular diagram, these two corners will be bearing the brunt of that wind, and then in this case, a flank wind, then these two corners will be enduring the brunt of the wind. Now, what you generally want to avoid if you're designing a large structure is what's referred to as a quartering wind, in which you have a strong wind that's hitting the building at an angle. In the case of a quartering wind, then you have one corner of one point in the building that's bearing all the force of that wind, or most of the force of that wind. And ideally, this is something that you want to avoid. So again, this kind of goes back to knowing what the wind patterns are. So ideally, you want to have two corners bearing really strong winds. If the wind's really weak, then you don't have to worry about this as much. But if the wind is you want to know from what direction the winds are usually strongest, so that you can sort of angle your building in such a way where you can have two corners of the building that are bearing the brunt of those really strong winds, because you don't want a really strong quartering wind, because that can put a really intense strain on your building and possibly not end so well for your building. But that's going to do it for this final segment on Lecture 26, sort of tying meteorology and urban development, just kind of looking at an overview of those two subjects and how those two fields can sort of overlap. And that's going to do it for Lecture 26. So with that, I will see you all in the next lecture.